called think fast, time control, and varying paradigms of spiking neural networks. So for introduction, we know that deep learning models continue to grow and show improved performance. However, power consumption continues to increase. Spiking models provide a way to reduce this power consumption, but we lose accuracy when we go from analog to spiking models. So here we discuss methods of achieving A&N performance with an SNN, and we also propose models that we expect to be able to run on neuromorphic hardware. So an overview of a couple types of spiking neurons. Integrate and fire neurons are spiking neurons whose firing rates can be given as a function of input times a time step. And introducing a leak term tau greater than 1 into this transforms it into a leaky integrate and fire neuron, whose firing rate can be given by input voltage over tau times a time step. In order to test our models, we did traditional MNIST classification using an MLP classifier with 3 fully connected layers and a ReLU activation. The task and architecture were chosen based on their presence in the Lava tutorial for Intel's neuromorphic chip, Yijing. We transferred the A&N weights from this training model to our SNN models and measured their classification performance. Here's an overview of our methodology. So on the left is a schematic that represents our multi-layer perceptron. And we replaced the nodes in this network with one of the 3 types of models shown on the right, the rate code, the ensemble models, or the accumulator. Going from left to right with these models, they become less biologically plausible, but give us better inference times. So the first model I'll talk about are the rate coding models. We converted the ReLU A&N to spiking model by sending weighted inputs as current to the either integrate and fire or the leaky integrate and fire neurons, as shown by the equation on the slide. We then measured the average firing rate as an output. We ran these for variable numbers of time steps from 10 to 100 and determined the accuracy. On the plot here, the black line represents the non-leaky firing rate-coded model, and the blue line represents the leaky rate-coded model. So as you can see, the non-leaky model outperforms the leaky model, and its accuracy improves more quickly as a function of the number of time steps. So the next model that I'll talk about are the ensemble models shown in the middle here on our overview. The first ensemble model is called ION for interfering offset neurons. If you look at the schematic on the top right, you can see that one input is sent to all 3 neurons in the ensemble. These neurons are different in their bias currents. So one has a negative bias, the other has a positive bias of equal magnitude, and the other is neutral. These outputs are then summed and interpreted as a single node in our network. Shown on the bottom right is an example of input and output from this model. In orange is the activity of the ION model, and green is the activity of a ReLU. So when the input exceeds the threshold minus the bias, we get activity from 1 neuron. When it exceeds just the threshold, 2 of the neurons fire. And then when it exceeds the threshold plus the bias, we get activity from all 3 neurons. And one of the advantages of this implementation is it can be adapted to allow for graded output for negative inputs as well to give us a negative output. But for here, we're just approximating a ReLU function. So this is how we utilized it for this classification. The next ensemble model that we tested was the life ensemble neuron model. Here, input is sent to neurons that differ based on their thresholds, and the outputs of these neurons are weighted based on the threshold of the input. So in the bottom right shown is a similar plot of the input and the output. The blue line again represents a ReLU. So you can see that between 0.1 and 0.2, the weighted output from this model is 0.1, and then from 0.2 to 0.3, proportionally weighted at 0.2, and so on. And for our ensemble models, we also ran for a variable number of time steps from 10 to 100 and compared the accuracies. On this graph, the yellow line represents the ION model, and the red line represents the LEN model. So our non-leaky ION model, again, performed better than our leaky LEN model, and its accuracy also increased more quickly as a function of the number of time steps. So lastly, I'm going to talk about, in terms of our models, the accumulator models. So accumulator neurons allow for graded output by providing multiple spikes per time step, and increasing the maximum number of spikes per time step increases our accuracy. So if you look on the right, another way to think about increasing maximum spikes per time step is thinking about it as spike amplitude. So as the spike amplitude decreases going down, you can see that the accumulator neuron does a worse job at approximating the function and is spiking less frequently per given time step. So we tested both leaky and non-leaky accumulator models. And so in the bottom left, you can see the yellow line is the non-leaky accumulator, and the red line is the leaky accumulator, with, again, the non-leaky model performing better and having its accuracy increase more quickly. So we saw that the non-leaky models perform better than the leaky models, and we tested to what extent increasing our leak constant had on our accuracy. So in red, we show the accumulator model, and in blue, the rate-coded model. You can see that the accumulator model is more robust to increases in the leak rate constant, but both models showed decreasing performance as the tau value from the earlier function increased. So these approaches use naive models, simply transferring the weights from the ANN to the SNN. We wanted to test what accuracies we could achieve with the SNNs by training them directly with stochastic gradient descent. So we had to use different gradients for each of these models in order to do backpropagation. So the ensemble models generally approximated the ReLU function and thus had a similar gradient to that of ReLU. For the LIF firing rate and the IF firing rate, recall that it's given by the input over tau times the time step. So differentiating this with respect to the input gives a gradient for the rate-coded models, which is the time step over tau. And then if we treat the accumulator model in a similar way, but since they're putting multiple spikes in a time step, we set t to 1 and then integrate with respect to the input. Then we get the gradient for the accumulator models, which was the input over the tau decay constant. So here are the results from our different classification tests. On the left, the models are separated by different types. So we have the ANN at the top, the two rate codes, the accumulator models, and then the ensemble models. So you can see that for the simple weight transfer, the non-leaky accumulator was able to give us the same accuracy as the ReLU ANN, so it was able to approximate it very well. This is allowing it for 100 spikes per time step. Running the rate codes for 100 time steps, the leaky rate code still showed a significant decrease in performance compared to the ANN, but the non-leaky rate code was able to get very close performance. The ensemble models were also able to give fairly good performance compared to the ANN when just transferring the weights. And then for custom training, the range shown for the ReLU ANN is the different accuracies when running 10 different iterations of training with different random seeds, just to give us a different range for stochasticity. And all the SNN models trained with their own gradients were able to get essentially the same accuracy as the ANN. For inference time, I measured the number of time steps for each model that was required to match the accuracy for the leaky rate code at 100 time steps. So that one is run for 100. And you can see that the non-leaky models have shorter inference times than the leaky models. And the models that are more biologically plausible, like the rate code model, showed longer inference times, and then followed by the ensemble models and the accumulators with the shortest inference time. And then for a relative measure of power consumption, I looked at the number of spikes per time step for these models when run for the number of time steps in the inference time column. So the non-leaky models tend to show greater power consumption than the leaky models, with exception of the rate-coded models. And we see high power consumption for our ensemble models because they're consisted of multiple neurons per node. So in conclusion, our SNN models were able to match the ANN accuracies, and the non-leaky models gave better performance but required more power. And this is considering, for spikes per time step, the accumulator, a single firing was considered as one spike, analogous to like an integer payload on neuromorphic hardware. Our models allow for a trade-off between speed, accuracy, and power consumption, and additionally allows us to try different biologically plausible models. And we expect that our models should be implementable on neuromorphic hardware. So our next goal is to transfer these models onto neuromorphic hardware. We've already implemented the rate-coded model on Luihi, and the consideration for implementing our other models on Luihi involves sparsity in connectivity and spiking activity. We also plan to test these models on additional data sets and time-varying data, and we plan to use them for on-chip dictionary learning on Luihi. So I'd like to thank the Department of Energy for their financial support, and thank you for listening.
All right, thank you. Very interesting talk. Any questions from the audience? Well, I have one to get us started. I'm just curious what you think about this discrepancy between the leaky and the non-leaky neurons and why there's such a big performance gap.
So I think, so for the accumulators, the discrepancy in the leaky and the non-leaky performance is when they saturate to the input value, they still oscillate. And the leaky model oscillates more often than the non-leaky model. So that's why occasionally you get an incorrect value more often. And then I just think since the spiking activity is more sparse, there's less chance of getting an accurate result. I just don't think they approximate as well, but when you custom train the models, it is able to adjust for it and get similar performance.
Thank you.
Great talk. Do you expect that there would be different performance, maybe for example, in the leaking versus non-leaking for the time varying data sets that you're planning to apply?
Since the leaking models have more of like a delay, I would think that they would perform not as well, but I can't say for sure because I haven't tested that.
Okay, any other questions? All right, let's thank the speaker once more.
Hello, everyone.